Welcome back. The objective of this video is to explore one-to-one properties of logarithmic and exponential functions. We'll solve exponential equations algebraically. We'll solve logarithmic equations algebraically. And we'll also solve an exponential equation that each side has different bases. So let's consider the following equations. We have 2 to the x equals 64 and log of 3x equals log of x minus 8. We can use the one-to-one properties below to solve equations algebraically. But how do we handle the more difficult equations and inequalities? Well, here's an example of the one-to-one properties. For any exponential function, y or f of x equals b to the y, then b to the u equals b to the if b to the u equals b to the v, so meaning if we have the same base, well then the exponents must be equivalent, which totally makes sense. That if we're going to have the left side equal the right side and the bases are the same, then the exponents on the left has to equal the exponents on the right. Similarly, for a logarithmic function, if we have log base b of u equals log base b of e, so our bases again have to be the same, then of course u must equal v. So here's an example of solving an exponential function using the one-to-one properties. But we don't have the same base here with 2 and 64. But 64 can be rewritten and get this into base 2. So we have 2 raised to the x minus 5 equals 2 to the 6th power. So now that our bases are the same, we can simply say x minus 5 has got to equal 6. The exponent on the left has to equal the exponent on the right. And we solve for x, and we get x equals 11. In the same manner, in 1b, we have log of x equals 2 log of 2, and we want to solve this for x. Well, we have base 10 here. We can reverse the power rule and put those guys back. X to the 1/2 is the same as the square root of x. So log of the square root of x equals log of 2 squared. So 2 squared, or 4, has to equal the square root of x. So the square root of x has to equal 4, and then we can square both sides to undo that square root or do the inverse operation. There's a blast from the recent past. So we square both sides and we get x equals 16. So show that work, show your understanding, show your algebra, work down the page. Moving on, real quick in our notes, an exponential equation is an equation that has an exponent in it. And the exponent is, or the variable is in the exponent. A logarithmic equation is an equation that includes a logarithm involving a variable. So let's solve these equations algebraically. In example 2, we have 24 times 1/2 to the x over 3 equals 6. We'll start by dividing both sides by 24. We want to strip things away from that, from our base of 1/2, or that could be looked at as 2 to the negative 1, which we might do. So we get 1/2 to the x over 3 equals 1/4. And 1/4 is the same as 1/2 quantity squared. So we can get the same base here. We don't have to change our base. We can leave it as 1/2. And 1/4 is 1/2 squared. So now we have the same base. So we can drop our 1/2 base. We can say x over 3 equals 2. Multiply both sides by 3. And we get x equals 6. In the logarithmic equation, let's go ahead and take a look at that. I'm going to take this 2 and invoke that power rule again. So we're going to have log base 3 of x squared equals log base 3 of 4 cubed. So I've got my answer has to equal my answer because I've got the same base or the same log base here. So I can simply say x squared equals, well, 4 cubed is 64. Inverse operation of x squared is the square root. So I get x equals plus or minus 8. However, x can't equal negative 8. We can't have a negative answer in our original equation here. So we're just going to say x equals 8. That's our positive answer. In examples 4 and 5, we can use the definition of a logarithm to rewrite exponential equations in order to solve. So here in these problems, we're going to flip between logarithmic and exponential form to solve. And how I remember that is if I only have a logarithm on one side of the equation and not both sides, then I know that I'm going to switch forms. So here in example 4, I have log base 2 of 4x equals 5, log base answer equals exponent. I can't log both sides, I can't square root both sides, so we'll go ahead and switch forms. So we're going to go from logarithmic to exponential form, so we can say 2 to the 5th equals 4x. Well, 2 to the 5th is 32 equals 4x. Divide both sides by 4, and we get x equals 8. Again, notice I'm working down the page. My equal sign is kind of a center point here, so showing my algebra nice and neatly the way you were taught in the younger grades. Please continue to use those good habits. In example 5, we're going to do a similar kind of thing, but we're going to apply our properties of logarithms here. Addition of logarithms is multiplication, so we can rewrite this as log base 10 or log of x times x plus 15 equals 2, which is log of x squared plus 15x equals 2. Now I'm going to rewrite this in exponential form. Our base here is 10, so the exponent on 10 is 2, so x squared plus 15x equals 10 to the second, or 100, so x squared plus 15x. I've got a quadratic, so I'm going to have to factor or use the quadratic formula. I'm going to subtract 100 from both sides and set that equal to 0 and go ahead and factor. I need factors of negative 100 that add up to 15, and sure enough 20 times 5 will do that. So I get x plus 20 times x minus 5 equals 0, and I end up with x equals negative 20 and x equals 5. Again, x can't be negative 20, so this guy can't be negative. So our final answer here will be x equals 5, and x equals negative 20 is an extraneous root. Real quick, before we move on, again, this is an equation, so it stays an equation the whole time, even when I'm factoring. Again, working down the page and using my equal sign as kind of a vertical line here, so keeping everything in order and working on both sides. Another good modeling of what I expect to see in your work when you solve similar problems. In examples 6 and 7, we're going to solve exponential equations with different bases. Now, we don't have any logarithms on each side, so we're not going to change forms at this point, but let's take a look and see how we'll solve this. So in example 6, we want to solve 8 raised to the x minus 3 equals 26. We can't get the same base here. We're not going to do base 2 or base 8 or base 4. None of that's going to work for us. So in order to get that x minus 3 out of the exponent, we're going to have to log both sides. And we have options. We can do natural log if we want, or we could do log base 10 of both sides. I'm going to choose to do log base 8, and you'll see why. So we're going to log 8 both sides. And you've got to show that work. So log base 8, 8 to the x minus 3 equals log base 8 of 26. So we've logged both sides. So just like we can square both sides and square root both sides, and multiply both sides and divide, we can log both sides. So I've logged both sides of my equation, which allows me to apply my power rule. I can bring that guy down. Now keep in mind, we're bringing this whole quantity down, so parentheses matter here. So now we have x minus 3 times log base 8 of 8, and now you can see the beauty of that, equals log base 8 of 26. Well, log base 8 of 8 is 1, so now I just have, this becomes 1, so now I have x minus 3 equals log base 8 of 26. I can't do that in my head. I can add 3 to both sides, and I get x equals 3 plus log base 8 of 26. So this would be my exact answer. Okay? Without putting this into my calculator, I can then go ahead and put this into my calculator, and once I do that, the calculator, rounding to the nearest thousandths or 3 or 4 decimal places, x is approximately equal to 4.5668. Apparently I've gone 4 decimal places here. So log base 8 of 26 is a 1.5668. In example 7, we'll do a similar thing. E and pi are two of our favorite irrationals. Because we have e, though, I'm going to use the natural log. Certainly, you could do log base pi if you wanted to, but I'm going to do the natural log here, and that's going to be the inverse operation of e. So I natural log both sides and bring that x down in front. So we'll show that work. So natural log of e to the x equals the natural log of pi to the 1 plus x, and that's a quantity. So the power rule lets me bring both of these guys down in front. So I have x natural log of e equals the quantity 1 plus x natural log of pi. The natural log of e is 1. So now I have just x equals, and I need to get all my x's on one side, so I'm going to distribute my natural log of pi. So I get the natural log of pi plus x natural log of pi. That's multiplication. Subtract that guy from both sides. So I get x minus x natural log of pi equals the natural log of pi. I factor out my x, so I get x times 1 minus the natural log of pi equals the natural log of pi. I've isolated my x, so I can divide both sides, and I get x equals the natural log of pi over 1 minus the natural log of pi. And that is my exact answer. And an approximate answer, by putting this into my calculator, I get x equals negative 7.909. And x can be negative here. I can have a negative exponent. That's legal, so I've got a legal answer, and I got that by using my calculator. And in this final example 8, we can solve with using a graph or a table. So we can put both equations into our graphing calculator. So 2 to the 3x, we do y1, and y2 equals 9. And then we would graph both using the Windows, and then find the intersection, and that's under the calc menu, and I think it's choice 5, and then I think you have to hit enter 3 times, enter, 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 and it'll give you the intersection. We don't want to trace. So no tracing. And then we can also do a table setup, and that's above the window key. So again, put both into your equation, and so we can, or into your graphic calculator, and under second window, we can do a table setup and start our table at 1, and our change in table is 0.01, and then once you do that, you can go to second graph, which I think has the table key above it, and then it'll give you the table and you can find your answer. So there's an introduction to solving exponential and logarithmic equations. So lots of algebra. Make sure you're good about showing your work. Working down the page is super important to me, and using that equal sign as a balance. And we'll get some more practice with this when I see you in class.